Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again. Thank you for joining us on the podcast known as Space Nuts. My name's Andrew Dunkley, and joining me every week is astronomer Fred Watson. Hello, Fred.
Hello, Andrew. How are you going?
I am well. Good to see you. In fact, we have a funny story. A couple of weeks ago, you had to come to Dubbo to be a guest speaker for the National Science Challenge with high school students. And because of the timing and the placement of things, we were only a kilometre or two apart, but we couldn't see each other for a cup of coffee or whatever. Last week, I had to be in Sydney. I walked past your office, but no one was home. That's two near misses. We're like exo-asteroids, Fred.
That's right. One day, space and time will come together and we'll have a cup of coffee.
Sounds like a plan. Now, today we're going to talk about some clues in the search for the origin of life, which is a pretty complicated story, but fascinating too, because it could actually mean some pretty exciting things are happening out there. If all holds true. We're also going to look at the discovery of a giant world, but they're not sure if it's a planet or a star. Well, that's confusing. And we've had a question from Andrew Mitchell about photons, which we're going to get to a little later. Thank you, Andrew. First up, though, Fred, the search for the origins of life. This is the ongoing search and battle for the truth. And now they've come across something that might just suggest there's more life out there than we originally could have considered.
That's absolutely right, Andrew. I think we're living a really exciting time in terms of our understanding of how life originated on this planet. And of course, anything we discover about that has implications for the astronomical world, for the possibility of life elsewhere. So there are two competing theories about where life kicked off on Earth. They both require there to have been a sort of, a reservoir of what we call prebiotic molecules, molecules containing carbon, the kind of things that eventually go together to make RNA and later DNA. So the two theories are that either life originated in what is sometimes called warm ponds, but by that I guess you mean places where there is hydrothermal activity on the Earth. And there are a number of places, and I've visited some of them, where there are things like geysers and
black smokers, or whatever they're called.
Well, black smokers are the other theory. These are the sort of warm pond theory says that this was on the surface of the Earth. It was on the land. Right. That where there's hydrothermal activity, the kind of things that are going on in New Zealand. You've got geysers and these various forms of geothermal activity. That they were rich in chemicals. They provided heat, and that's where life might have triggered. And in fact, there's been some work recently done in a place called El Tatio, which is the highest geyser field in the world. I've visited there. It's in South America, actually, in far northern Chile, in the Atacama.
Yeah, I've seen the geysers, or one of the significant geysers in Rotorua in New Zealand. It's just staggering the way it all works.
That's right, they are.
And the heat that comes off the ground there, or out of the ground there, just mesmerising.
So that's theory number one, that was the kickoff for life. The El Tatio one, by the way, there are structures there called opaline silicates, which are thought to have been laid down by ancient organisms, and tantalizingly similar things have been seen on Mars by the Curiosity. Actually, it might not be the Curiosity, I think it might be Opportunity that found these rover on Mars. Anyway, we're not talking about that today, so you can forget all that, because the other theory is, as you mentioned, the black smokers, the hydrothermal vents, which are deep down in the ocean. And it's the same thing the same mechanism. It's water seeping down into the Earth's crust and being heated and then projected back up again. That's how geysers work, and it's also how black smokers work, the hydrothermal vents, the difference being one's on land and one's under the ocean. So one of those is thought to have been where life kicked off. The reason why we're talking about this today is that there's been some research done on modeling the kind of chemical effects of black smokers underneath the ocean, the hydrothermal vents, which suggests that actually some of these prebiotic molecules are much easier to form in the vicinity of these things. And in particular, if you assume that you don't just have one vent that's spewing out stuff, but that you've got several, and they're interconnected. They've suggested the existence of what they call long and networked pores through within the crust of the Earth. And it turns out that actually allows these what are called extended polymers. They're molecules that really lend themselves to the emergence of RNA. So if you have a lot of different pores emitting the hydrothermal vents, okay, you can call them pores, perhaps interconnected hydrothermal vents might be a better way to putting it. But when you look at the theory behind these things, if they're spread over a large area, what you get, and this is the crucial thing, you get variations in the temperature. The temperature in one of these vents will be different from one of the neighboring ones. And it's that variation in temperature that gives you the possibility of forming these complex molecules. If you've got too high a temperature, what happens is that the various catalysts and the molecules themselves are actually broken up before anything's happened. And if the temperature's too cold, nothing happens at all anyway.
Hello,
and
this is starting to sound like a nursery rhyme again.
Much of astrobiology sounds like a nursery rhyme, Andrew. But yeah, so the bottom line is that these conditions they suggest are actually with the interconnected pores, they're better fulfilled by the undersea hydrothermal vents than by the warm ponds, the little crater lakes and things of that sort.
Right.
And so what they're suggesting is that where there are hydrothermal vents, and particularly interconnected ones, a complex set of these things on the ocean floor, then you've got the perfect conditions for these complex molecules to form and possibly to trigger off the emergence of life. And that's that is the big step, because they then realize that hydrothermal vents may actually be quite common throughout the universe, and in fact quite common even in our solar system. We know pretty certainly that the under ice ocean of Saturn's moon Enceladus actually has on the ocean floor, it's buried under a layer of ice before you get to the ocean, but the ocean itself sits on a rocky floor, exactly as the Earth's ocean does. And there are almost certainly hydrothermal vents there, because we've seen the evidence for that in the plumes of ice crystals that spew out of Enceladus' south pole. They've been measured by the Cassini spacecraft.
Yes.
So it's very intriguing that we've basically got just a couple of clues here that maybe, well, first of all, maybe hydrothermal vents are commonplace, but also maybe the chemical reactions that lead to life might be commonplace as well, which is why this is quite an exciting piece of research.
So that 5-hour explanation you just gave us, basically the simplified version is we think there's a lot of these things, therefore there's probably a lot of potential for life in the universe.
That's correct. And I forgot to mention something that's rather a quirky aspect of this story. One of the things that's probably familiar to people, because it's used as, or it used to be used as hair bleach, hydrogen peroxide is one that is a crucial catalyst in some of these reactions. And that sort of pops out of the modelling that they do for this kind of thing.
We need to get that submarine up to our Enceladus very, very soon.
I think it's down to you and me, Andrew.
Yeah, pedal powered.
Pedal powered.
Would be the way to go.
Yeah.
I think they did that with the first submarines. But
Yeah.
it is exciting because it really does mean the search can be honed in on some specifics. And once you get that, you know where to look and you know what to look for. Your chances of finding some life are significantly increased, I would think.
Indeed, that's right. So forgot to mention this research was carried out at the ANU and also at the University of Leeds in the UK. And the researchers say that yes, we've been following the mantra "follow the water" for looking for the origin of life, but they suggest that we should also include the mantra "follow the temperature fluctuations" because it's those things that might lead to these molecules being formed.
Well, we know on Earth that critters do live near those black smokers.
Absolutely.
Life has adapted.
That's right.
So it's not beyond the realms of probability by the sound of it. Very exciting stuff, Fred. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Next up, Fred, we're going to look at a planet. Or is it a planet? Could be a star. Could be a star that thinks it's a planet. Could be a planet that wants to be a star but can't get a break in Hollywood. We're not sure. So what is this story about? And I'm guessing it's as complicated as what we were just talking about.
Yes. It's another interesting story. It relates to things that we can probably all get our heads around in terms of the objects that we find out there in the universe. So for many years, probably 30 years now, we've known of the existence of a species of star which you might call them failed stars. They're called brown dwarfs.
Ah, yes.
And they are. They were predicted theoretically, actually, before they were observed. And some of my colleagues in the what was then the Anglo-Australian Observatory were very interested in these objects and actually did a lot of research on them. So brown dwarfs are objects that have not got to the temperature required for what we call the fusion of hydrogen, and that's what makes the sun work. Let's just do star formation 101. You start off with a cloud of hydrogen, often mixed with dust, and the dust is what eventually makes the planet. The cloud of hydrogen collapses under its own gravity. The heat caused by that collapse. It's like, when you pump up a bicycle tire, the pressure goes up and the temperature goes up. Likewise, at the center of this collapsing cloud of gas, the pressure gets very high, the temperature gets to something like 10 million degrees, and that allows you to trigger the nuclear processes, the nuclear, actually what's called nuclear fusion, which is when hydrogen turns into helium, and that releases the energy which actually balances the gravity and causes the star, to become a stable thing like the sun is now.
Yeah.
Okay, that's a normal star. If you don't have enough hydrogen, you still get the collapse, but the temperature never gets high enough to go through this normal nuclear burning process. But there is a sort of intermediate stage, and that is something called deuterium burning. Deuterium is an isotope of hydrogen, and it actually reacts in a different way from the way a normal star reacts, but it does generate a bit of heat, and in fact it generates enough heat to form one of these brown dwarf objects. Mm-hmm. So typically they are 40 to 50 times the mass of Jupiter. That will be the typical mass of a brown dwarf star.
Okay.
And the sun is, many thousands of times the mass of Jupiter. So you can see it sits in that lower mass range. But there is a cutoff defined. Anything that is smaller than 13 times the mass of Jupiter cannot have enough gravity to cause deuterium burning. And so that is not a brown dwarf. It's a big planet. So something less than 13 times the mass of Jupiter is a planet. It doesn't have this. It actually does have internal heat sources, but they're not caused by deuterium burning. And so they don't get to glow in the infrared region of the spectrum, the heat region of the spectrum, which is how we detect brown dwarf stars.
So I'm guessing we've found one of these?
We've found one whose mass is, guess what? 13 times the mass of Jupiter. So it's right on the limit.
On the cusp.
On the cusp, yeah. The boundary that says on one side of that boundary it's a planet, on the other side it's a star. And so this thing sits right on that boundary. It's an object that was discovered in an interesting way by a project called OGLE, O-G-L-E, which is an acronym, of course, for Optical Gravitational Lensing Experiment. It's a Polish project, but actually has...
That's a pretty good name.
It's a great
done
one,
well there.
Yeah. They're ogling the universe. You'll notice, Andrew, that in that acronym, the OGLE acronym, the words gravitational lensing are included. And that refers to the idea that a planet or a star which has mass, like everything that has mass, it distorts the space around it. The Earth does that, and it's actually that distortion that we feel is the pull of gravity. But in this case, what's happened is that this planet has acted like a gravitational lens. It's bent the light from a more distant object around it, but the distant object is actually the star which this object is orbiting around. I know this is a complex and difficult thing to explain without diagrams, but what you've got is a star. You've got its planet which passes in front of it. And paradoxically, instead of blocking out the light from the star, it actually magnifies the star because it's big enough to act as a gravitational lens. And that's what the OGLE astronomers see. They see a peak in the brightness of the star as a planet passes in front of it. So that is how this object has been discovered. And what it means is that they know more about this thing than we normally would with OGLE objects. Often the planet passes in front of a distant star and you never see it again. But this particular one is in orbit around its parent star, and they think it's got an orbit of around 3 years. So in 2019, they're hoping to get another look at this thing and maybe find out a bit more about where it sits on the, on the scale of planethood or starhood.
Yeah, interesting. So it could be a binary star system, or it could be a planet orbiting a star, and it's just a mega massive planet.
That's correct. That's right. One of the things that's kind of even more intriguing about this is that if all the calculations are correct, this thing sits at something like, if I remember rightly, I read these figures earlier, something like twice the distance of our Earth from the sun in its orbit around its planet. And if it's a brown dwarf, that's very unusual because this has never been seen before. And it's thought to be all about the way brown dwarfs form. So that tends to push you towards the view that this is actually a planet, not a brown dwarf.
Yeah, I'm wondering what it would be like to stand on. Obviously, it would be pretty hostile by the sound of it.
Well, it's more like, I guess what you've got to imagine is what would happen if you were trying to stand on Jupiter. Jupiter's a gas giant,
can't
so
do that. Yeah,
solid surface. And brown dwarfs are just like giant Jupiters, but they're hotter. They release more energy because of this deuterium burning process.
Sounds
it's complicated stuff, but it is nasty. But one of the other things that clouds the boundary between brown dwarfs and planets is that brown dwarfs have weather. They actually have weather in their atmospheres, and I've even read papers that suggest that actually the weather is such that you get showers of rain, but the rain is not water; it's liquid iron droplets.
Whoa, wow! Yeah. BHP would be thrilled.
Yeah, well, it'd probably give a whole new idea to what kind of things you might make umbrellas out of.
Yeah, I don't think anything would last long under one of those. Yeah. Exactly. That's fascinating. All right, so we've got to wait a couple of years before we can find out. At this stage, the jury is out, but leaning towards planet.
I think that's right.
All right. We'll know more in a couple of years, and we'll be here to tell you about it. Theoretically.
Hopefully.
You're listening to Space Nuts with Andrew Dunkley and Fred Watson.
3, 2, 1.
Space Nuts.
Last but not least, Fred, we have a question from one of our 4 listeners. Andrew Mitchell, you and I are included in that statistic, by the way.
Yes, I thought we might be. I think it was pretty optimistic.
I was just watching a YouTube video which mentioned the recent publication about that newly discovered 13 billion year old galaxy, and a question occurred to me. It's about redshift. So, say a very distant sun emits a photon at the blue end of the spectrum. On its way to us over billions of years, it gets stretched and we see it as a red photon. Now, the red photon has less energy than it had when it was a blue photon. What happened to the energy of that photon? Andrew asks.
It's a very good question. Actually, that's a very well posed and absolutely, right smack on the money question.
Well, maybe for my benefit, we should start by explaining.
I was going to do that.
I thought you would.
Not so much for your benefit as for the benefit of me and all the other listeners who've got to get their heads around this sort of thing. So it's absolutely right. What is said there is perfectly true. You have a universe that is expanding. We have radiation going through it. It's not just light. There's X-rays, gamma rays, radio waves, lots and lots of things going through this radiation. But the bottom line is that if light or whatever it is travels long enough through the universe, the expansion of the universe itself stretches the light waves or radio waves or whatever they are. And the term we use for that is redshift. It's the reddening of light caused by the expansion of the universe, but it also applies to other radiations. Now, there are 2 ways of looking at light. In fact, pretty well all electromagnetic radiation. You can either think of it as waves, waves traveling through a medium which actually isn't there, but waves traveling through space. Or you can think of it as particles of light. We call them photons. And in fact, both are correct. That's one of the peculiarities of quantum mechanics, that in quantum theory, things can be either waves or particles. But the bottom line is that as the universe expands, it doesn't matter whether you think of them as waves or photons, they basically get longer, the wavelength gets longer. Photons themselves have a defined energy which is related to the wavelength of the wave. The universe expands, so the light is reddened, which means that the photons have lost energy because blue photons have more energy than red photons. That's the crucial part of this. What the expansion of the universe does not do is slow down the photons. Through space, everything travels at 300,000 kilometers per second, the speed of light. But the expanding universe takes away energy from the photons. So it turns a blue one into a red one, a high energy photon into a lower energy. For the benefit of our listeners, I can see that you are nodding as I'm saying this, which means
that's me pretending to understand.
Maybe I'm saying things that people can understand. So the question, exactly right, what happens to the energy that they lose?
Yep.
And I've kind of hinted at it already. It basically goes into the expansion of the universe. As the universe expands, it's drawing energy from everything that's traveling through it. And that is actually another way of looking at it. The expanding universe is drawing energy out into its own sort of reservoir of an expanding space. And the effect of that is to redden the photons, to take these blue photons and turn them into red light.
Simple as that.
It is, yeah. But it's a great question, and it's one that does demand a little bit of thought. You can it's probably easier to think of it the other way around. If we're in a contracting universe, that's sort of analogous.
Would happen?
Well, yes, that's right. The photons would get more energy, so they'd be blue shifted. And what then you will be seeing is the work that's going into contracting the universe is actually being translated into the energy of the photons. It's very much akin to an analogy we've already used in this segment, which is a bicycle pump. Because if you pump a bicycle up, you're compressing the gas in it, and that gas is increasing in temperature. It's getting a higher energy. It's a very similar analogy.
Okay. It does prompt a question in my mind, though, about the expansion of the universe. If it's drawing energy from photons, is that what's continuing to power the expansion, or is the expansion still the aftermath of the Big Bang? I mean, surely something as big as the universe can't be continuing to use one energy source.
But in a sense, it is, because the Big Bang itself was an enormous release of energy, most of which in the early stages was in the form of radiation, so it was photons. That is what kicked off the expansion of the universe. There's something else weird that happened, which we call inflation, a very rapid expansion in the first few tiny instants of the universe.
That's where the bike pump came in.
That's right. That seems to be something to do with gravitational, actually, more than radiation. But yes, radiation is certainly one of the contributors to the expansion of the universe.
Okay.
A very good question, Andrew, if I may say so.
I do come up with one every couple of years, apparently. All right, Fred, thank you as always, and thanks to Andrew Mitchell for firing off that question to us. We do have a few questions we probably need to get to at some stage, but we'll work our way through them. Thank you, Fred.
Great pleasure, Andrew. Always good to talk to you, and especially to get these listener questions.
Indeed. And that's Fred Watson from the Australian Astronomical Observatory. Joins us every week on Space Nuts. And thank you for joining us every week as well. And keep those cards and letters coming in, or Facebook questions, or whatever you like. We love to hear from you, even if you just have a remark to make, or some people send us links to things. We got a link to a story about Leica the other day, Fred, so I'll send that to you.
Oh, good.
And whatever else. We're on Facebook, we're on Twitter, we're online, and we're at your disposal sometimes. If you do want to ask a tricky little question, don't ask me. But you can join us again every week, and we'll catch you again next week here on Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.